Welcome back to UBG Bytes.
Good to be back.
So today we're diving into something really central for, well, for us and probably for you listening. Large vision language models, LVLMs.
Yeah, these combined vision and language systems, super powerful, but they come with their own set of challenges.
Exactly. Specifically, we're looking at hallucinations in these models, where they just confidently state things that aren't true about an image. It's a major vulnerability, especially from a security and trustworthiness perspective.
Absolutely. If you can't trust what the model says it sees, its utility in critical applications just plummets.
Precisely. So we're digging into some recent research today, a paper proposing a method called EMPO, that's Entity-centric Multimodal Preference Optimization.
Right, EMPO. The core idea is to try and make these LVLMs more factual, more grounded in the visual reality they're supposed to be interpreting, basically more trustworthy.
Okay, so before we get into MPO itself, maybe we should quickly unpack what LVLMs are technically and why these hallucinations happen.
Good idea. So think of an LVLM typically having two main parts. You've got a visual encoder, maybe something like CLIP, that digests the image into numbers.
Right, features.
Yeah, features. And then there's a large language model backbone, like a Llama or Vicuna variant, that takes those visual features plus your text instruction and generates the response.
And the training is usually a two-step thing.
Generally, yeah. First, pre-training on huge data sets of image-text pairs. That's where it learns the basic connections like, this looks like a cat, corresponds to the word cat.
Building that visual semantic dictionary, essentially.
Kind of. Then comes fine-tuning, often with instruction data, teaching it to follow commands related to images, describe this, what color is that, etc.
Okay, and the hallucinations.
Yeah.
They seem to have a couple of flavors in these multimodal systems, according to this paper.
Right, the NPO paper breaks it down, referencing their figure 1, the first type they call modality misalignment.
Modality misalignment. What's that mean exactly?
It's where the model sort of sees something as there, an entity, but it misunderstands the specifics. Like, the example they give is a sign in an image. The LVLM knows it's a sign, it recognizes that object, but it reads the symbol wrong. It says no parking, when the image clearly shows a no motor vehicles symbol.
Ah, okay, so it connects the visual object sign but maps it to the wrong semantic concept in language. Got it. Dangerous if you're relying on it for detail.
Very. And the second type is maybe even trickier. LLM, inherent hallucination.
This sounds more like the standard LLM problem, but with a twist.
Exactly. It's where the language model part leans too heavily on patterns it learned from text data, even when the image contradicts it.
So like the figure 1b example, the road with no car.
Precisely that. The query is there a car on the road? The image shows, well, no car, but because car and road appear together so often in text,
the model just assumes there must be one.
Yes, it confidently answers, yes, there is a car driving on the road, completely ignoring the visual evidence. It's hallucinating based on text priors.
Wow, that's a fundamental failure of grounding. And the paper argues that existing methods like standard preference alignment haven't really fixed this.
Yeah, the critique is that methods like DPO, direct preference optimization, have mostly focused on optimizing the final response. Like, is the sentence overall good or bad?
But not necessarily drilling down into why it might be subtly wrong.
Right. They often neglect that fine-grained alignment between specific parts of the image, specific entities, and the corresponding words in the instruction or response. They don't robustly address those two root causes, the modality misalignment and the LLM's tendency to just make stuff up based on text.
Okay, so that sets the stage nicely for MPO. How does it try to tackle this differently?
MPO's core idea is this entity-centric focus across multiple preference dimensions. Not just the final response, but also aligning the image itself and the instruction.
Okay, entity-centric multimodal preference optimization. So focusing on the things in the image and making sure the alignment holds across vision, instruction, and response.
Exactly. And a really key part of their approach, something crucial for practical application, is how they generate the training data.
Ah, the preference data. You need pairs of good chosen and bad rejected examples, right? Which is normally a pain to collect manually for multimodal stuff.
A huge pain. Very expensive, very slow. So MPO uses an automatic data construction pipeline, leveraging existing open source data sets, no manual annotation needed, which is a big deal.
Okay, clever. How does that work? Let's start with the images. How do you automatically create a rejected image that's wrong in just the right way?
So they take an original image instruction response triplet, that's the chosen sample. To make a rejected image, first they identify the key entities in the original image. They use object detectors, but also even GPT-4o Mini to get a better contextual understanding of the scene.
Okay, find the important things. Then what?
Then they use a generative model, Stable Diffusion 2 in their case, to edit the image, focusing on those entities. They have two main strategies. One is entity deleting. Just remove some percentage of the detected entities, say 30%.
Okay, make things disappear.
The other is entity replacement. Swap an entity for something else plausible but incorrect. The paper has that great example in Figure 3, replacing a lion with a dog.
Right, visually similar structure maybe, but factually wrong. And they check that these edits actually worked.
Yeah, they use CLIP embeddings to verify that the edited image's representation is significantly different regarding the changed entity. These edited images, paired with the original correct instruction and response, become hard negatives for the visual alignment.
Hard negatives, meaning they force the model to look really closely.
Exactly. It has to learn to distinguish the original from these subtly wrong versions, forcing it to focus on specific entity details. Is it present? What is it really?
Makes sense. So that handles the image preference. What about creating rejected instructions?
Similar principle, but editing the text. They use GPT-4o Mini again. The goal is to change the original instruction so it's semantically different, especially regarding entities, but keeps a similar sentence structure.
Why keep the structure similar?
The thinking is that just using random nonsense instructions isn't as effective. By keeping the syntax close, but tweaking the meaning, changing entity names, attributes, relationships, you create instructions that look plausible, but are factually wrong for the given image.
Ah, so it forces the model to read the instruction carefully and not just pattern match vaguely.
Precisely. It acts as a hard negative for instruction following, making the model pay closer attention to the details, especially entity-related details, in the prompt.
Okay, image negatives, instruction negatives. What about response negatives? How do you get bad answers automatically?
They used a couple of techniques tied to specific data sets they built or used. For one called POVID, they actually fed the rejected images or instructions into an LVLM and used the incorrect response it generated as the rejected response.
Using the model's own failures, essentially.
Kind of, but a more effective approach they found, used for their RLA-FEFV dataset, was using a separate capable evaluation model, Mini-CPM v2.5, to simply rank several possible responses generated by different LVLMs for the original image instruction. The lower-ranked ones become the rejected samples.
Okay, using another AI to judge the quality. So this whole pipeline gives them automated chosen rejected pairs across images, instructions, and responses, all centered around entities.
Exactly. It's a pretty slick way to generate the structured data needed for the next step, the EMPO training.
Which builds on DPO, direct preference optimization. How do they make DPO multimodal and entity-centric?
They define the total MPO loss as basically the sum of three DPO losses. There's LDPOV for the visual part, comparing the original image preference against the rejected image.
Right.
Then LDPOQ for the instruction preference, comparing original versus rejected instruction. And finally, LDPO for the response preference, comparing the chosen response against a rejected one.
So optimizing preference across all three components simultaneously.
Yes. The model is trained to like the chosen image, instruction, and response together and dislike pairings involving the rejected versions.
And they added something to tackle reward hacking, right? This fine-grained entity weighting. What's that about?
Yeah, reward hacking is always a risk with preference optimization. The model might find clever ways to get a good preference score without actually being more factual, like maybe it generates grammatically nice sentences that still contain hallucinations about entities.
He learns to game the judge.
Pretty much. So the entity weighting tries to prevent this. When they calculate those DPO losses, especially for the instruction and response parts, they give more weight to the specific words, the tokens, that correspond to the critical entities identified earlier.
So errors related to those key nouns or adjectives cost the model more during training.
Exactly. It uses a hyperparameter, alpha, to control this weighting. You're essentially telling the loss function, pay extra close attention to getting these entity words right. It forces the model to ground those specific terms more firmly in the visual and instruction context.
Makes the penalty higher for hallucinating the important stuff. Did they find an optimal weight?
They did some analysis shown in Figure 4. It seems an alpha around 0.7 worked best.
Yeah.
So you need that entity focus, but you can't completely ignore the overall sentence coherence either. It's a balance.
Okay, the methodology sounds solid: automated data, multimodal preference, entity weighting. The critical question, does it actually work? How much does it reduce hallucinations?
That's the million-dollar question. They tested it extensively. Table 1 in the paper covers the trustworthiness results measuring hallucination reduction, using benchmarks like CHAIR, Hall Bench,
And what did they find?
pretty significant improvements. Compared to their baseline, LOV 1.57b, especially when trained with that RLAIFE response data, showed, for instance, an 85.9% reduction in hallucination rate on Object Hell Bench.
86% reduction, that's huge.
It is. And a nearly 50% reduction on Hell Bench, consistently large drops across different hallucination metrics.
How did it stack up against just using standard DPO without all the MPO modifications?
It beat standard DPO pretty clearly on these hallucination benchmarks, even when DPO is trained on the same preference datasets. This really supports their claim that the entity focus and the multimodal aspect are crucial.
So the specific MPO approach makes a real difference beyond just general preference tuning. Any comparisons to, say, commercial models?
Yeah, that was interesting. They found MPO achieved state-of-the-art trustworthiness among the open-source models they tested and actually outperformed GPT-4V on several of the specific hallucination benchmarks.
Outperforming GPT-4V on hallucination metrics, that's definitely noteworthy for an open approach. But the classic trade-off, did fixing hallucinations break anything else? Did it hurt the model's general usefulness?
Always a concern. They looked at that in Table 2 using general capability benchmarks like L of Bench for overall understanding and MME for perception and cognition.
And the verdict?
Mostly good news. MPO actually improved scores on L of Bench and the MME cognition parts. There was a slight decrease on MME perception, but it was still better than standard DPO on that metric too.
Okay, so it seems they managed to significantly cut down hallucinations without causing major damage to the model's general intelligence. That's really key.
Absolutely. You want factual and capable.
The paper also digs into why it works, right? Ablation studies.
Yep. Table 4. They systematically removed parts of MPO to see the impact. Removing any of the preference components, visual, instruction, or response, made hallucination rates go back up.
Proving the multimodal approach matters.
Exactly. And removing the entity weighting also slightly increase hallucinations, showing that component contributes positively too. It confirms the design choices were sound.
Did they find that how they made the rejected samples mattered, like the image editing strategies?
Oh yeah. Figure 3 and Table 3 touch on this. For images, the delete and replace entity strategies were much better than just, say, random cropping. They created those effective hard negatives.
Makes sense. And for instructions and responses?
For instructions, editing them semantically around entities worked better than just using random negative prompts. And for responses, using that evaluation model to rank outputs, RLAIFE, was superior to just using the outputs generated from faulty inputs, COVID. Quality of the negative data matters.
It really highlights the importance of crafting those negative examples carefully, even if automatically. And there was that visualization too, figure 5.
Right, the attention map visualization. It's a great illustration. They show the baseline Alavi model hallucinating a woman near a motorcycle. Its attention is kind of scattered, maybe focusing on irrelevant text cues.
But the MPO model?
Its attention map, when correctly identifying no person and describing the motorcycle, is much more focused. It's clearly attending to the actual motorcycle in the image and grounding its response in the relevant visual evidence. It's like you can see the improved alignment at work.
Providing some visual intuition for the mechanism. And does this tie back to the original hallucination causes they identified concept confusion and visual neglect?
It seems to. The entity-centric focus directly combats concept confusion by forcing precise understanding of objects and attributes. And the multimodal alignment, especially with the image preference and weighting, directly pushes back against visual neglect, forcing the model to ground its statements in the image, not just text patterns.
Okay, so summing up, MPO seems like a really well thought out, technically sound approach. It uses automated data generation to focus preference optimization on entities across image, instruction, and response, leading to significant hallucination reduction.
And importantly, state-of-the-art trustworthiness among open models, even beating commercial ones on some metrics, all while largely preserving general capabilities. It's a compelling piece of work.
And for listeners interested in exploring this themselves, the code and data are planned for release, right? That GitHub link, github.com/GMPO.
Yep, definitely one to watch if you're working in this space. A valuable resource when it drops.
Now, the researchers themselves point out limitations, future directions. They focus mainly on these entity-centric hallucinations, didn't they?
Right, getting objects and their immediate properties correct. But hallucinations can be more complex. They've mentioned needing to look into issues around common sense reasoning or how hallucinations might crop up in longer dynamic conversations.
Which is a whole other kettle of fish.
Yeah.
If the model has to maintain context over multiple turns.
Exactly. EMPO, as described here, is more about single-turn factual accuracy based on a static image and instruction. Interactive scenarios add layers of complexity state tracking, potential for context drift leading to new kinds of errors.
So that brings us to a final thought, maybe a question for you listening, especially given the security focus of this audience. We're seeing methods like MEU tackle these more direct, entity-level hallucinations. But thinking about those next frontiers, common sense gaps, errors, and long interactions, what do you see as the most critical attack surfaces, or maybe more constructively, the essential testing methodologies we need to develop? How should we as security pros be probing the trustworthiness of these LVLMs when they're embedded in complex interactive systems?
Yeah, it's a great question. If the obvious factual errors get reduced, where do we look next? Is it about crafting interactions that exploit subtle common sense failures? Or about seeing if we can poison the dialogue context over time to induce specific kinds of failures? How do we rigorously test these models not just on static benchmarks, but in dynamic, potentially adversarial interactions?
Definitely something to mull over as these technologies continue to evolve and integrate more deeply into critical systems. That's all the time we have for today. Thanks for joining us on UBG Bytes.
Thanks for having me.